So lesson 2.3 is kind of shifting, and now we're talking about collisions and mechanisms. And collisions is really big in AP chemistry right now. They like this whole collision theory, and there's always a couple of questions about just collisions in general. So a reaction takes place when, number one, molecules collide. So think about this. If two molecules are going to react, they have to actually come in contact to do anything. If they're too far apart to touch each other or too far apart to interact, nothing's ever going to happen. And so they physically have to touch, they have to collide. Number two, with enough energy. Have you ever tried to light a fire with two sticks? Without phosphorus. Most of you are aware of the concept. You somehow or another have two pieces of wood. Actually, it's better if you have 4 pieces of wood. But there's friction involved, and eventually it gets to the point where there's enough friction that it creates an ember, which is hot, and then you would put it somewhere else to make a fire. Now, if you're just watching TV, or if this is in your imagination, you're probably picturing like rubbing 2 sticks together and 10 seconds later having a nice fire. Where I told me none of you have tried this, I can tell you from experience that it's difficult to do, and it takes at least a half hour rubbing these 2 sticks together to get it hot enough. And the technique has to be just right. So I'm trying to get these molecules to collide between these 2 sticks and the oxygen in the air, and just rubbing 2 sticks together does not create fire. They don't have enough energy. So the molecules have to collide, yes, but they have to collide with enough energy to get the actual reaction. And number 3, they have to be in the correct orientation. So by this we mean that molecules are all 3-dimensional things. And so if one molecule and another react, maybe they have to react like this, where they have 2 specific parts touching each other. But let's say that one of them is turned around and hits the wrong side. And it can't react because the specific atoms that needed to touch didn't. And so they weren't oriented correctly. So the 3 main pieces of collisions here, they do have to collide, they have to physically touch. There has to be enough energy, and they have to be angled just right. How can we speed up the reaction? So I've got a handful of things here. What do you think we can do to make a reaction go faster? Add more molecules? Okay. So I'm going to say increase the concentration of reactants. Which is adding more molecules. What else do we do? More energy. Okay, so increase the energy. How are we going to increase the energy? At heat. Yeah. Increasing the temperature is how we increase the energy. Thank you, Megan. Thank you, Megan. couple of other ones. Nobody tried to rub two sticks together. Have you tried to light fire? Charlie used to match. Anybody else? All right. So is this like a bonfire on the weekend? Camping every now and then. All right. So Kyle, let me ask you this: if you're going to start a fire, start the fire, right? Yeah. Okay. So you're okay. How are you going to start this fire? Do you just like get a bunch of logs and throw gasoline on it, match? No. Nice. Not the best. What are you gonna do?
Put a bunch of little light pieces of wood and try to light that. They're lighter than the fuel.
Okay, so you're gonna start with some small pieces. Why do small pieces of wood work for you? Why don't you use big pieces?
Big pieces would take longer to ignite.
Take longer to ignite. What's the difference between one big piece of wood and 1,000 small pieces of wood? The surface area. Increase the surface area. Charlie, increase the surface area. In chemistry, how do we increase the surface area? So let's say I have this big chunk of a reactant and I toss it into a solution, it goes pretty slow. But if we want to increase the surface area, probably the best way to do it is to cut it up into tiny pieces, or maybe get out like a mortar and pestle, which is just this thing where you grind it up. You want to pulverize it, make it into the thinnest powder you can, and that's how you maximize the surface area. So the smaller the little particles, the more surface area it's going to have. A couple of other ones, I don't see anybody guessing this one. If it's gases, increase the pressure, which also tends to increase these two. If you increase the pressure, the volume is smaller, so the concentration is actually greater. If you increase the pressure, the temperature usually goes up. And the last one, from your biology class, have catalyst. Catalyst will speed up the reaction. If you remember, catalyst is not used up in the reaction. It's just kind of there. And it does some things, but at the end, it's still there. All right, so potential energy graphs is our next one. Here's what I'm going to write in. Potential energy graphs. Consider the reaction. We have A yielding B plus heat. Okay, so we're going to sketch the potential energy graph, identifying the potential energy of A, the potential energy of B, the potential energy of the transition state, the activated complex. Let's start off small. The potential energy of A and the potential energy of B. Here's the basic graph you have off to the side. So let's think about what happens. We have a reactant, and as it reacts, it's creating product and heat. Heat is being released. Remember the word from Chem 1, this type of reaction, basically. It's an exothermic reaction. So heat is being released. It's an exothermic reaction. So is fire. I keep talking about fire as huge. Fire. My firewood has a lot of potential energy. And then when the reaction starts, it's creating new products and a large amount of heat. And then at the end of the day, when everything is cooled down, I have the product left over. Some of it's white, some of it's black. How much energy does this stuff have? The gaseous. Are gaseous really good for anything? Not much. If I want to make another fire, the ashes aren't going to do it. They just don't have enough energy. So how is the energy of A related to B? My firewood has more potential energy than my ashes, right? And so let's just look at how they are starting off. Here's the potential energy of A, and maybe here's the potential energy of B. Maybe even lower than that, whatever. So here's what happens. I have my firewood, and my kids do this all the time lately. They see me starting fires in my fire ring, and so they have commandeered some of my bricks and made their own fire ring and piled the firewood all over it. What's the difference between theirs and mine? Mine is on fire, theirs is not. Yeah, it does have more potential energy. Why is theirs not on fire? Why is my kids' campfire not on fire and mine is? What I did differently? What do you think I did? Yeah, I don't give my kids a lighter. What is the lighter doing for us? Initiating reaction. In terms of one of these, what's going on here? We're increasing the temperature, or we are increasing the energy here. So if my potential energy of A is here, it doesn't just catch on fire. So let me do this in a different color. This is not what it looks like. It doesn't just slope down like this. It's not magic. Things don't burst in flames. I have to add a little bit. So I have to add some energy to increase it to a certain point. And then it slopes down like this. So this is what my potential energy graph looks like. I had a lot of potential energy. I had to add energy to catch it on fire. And as it burned, the energy was going away. And now my product, my ashes, has a lot less potential energy. Yeah, but that's not all that's going to go on this graph. The potential energy of the activated complex or the transition state. Let's look at activation energy first. Where's my activation energy on this graph? It's the spike. So it is from here, the potential energy of A, to the top of this spike where the reaction can actually start. From here to here, from here to here is the activation energy. Did you draw little dotted lines like I did? This came up in my conference too. So let me draw you the duplicate of this, more or less. Don't draw this one. They were talking about all the possible wrong answers. So the student was drawing a graph like this, where I think the graph was drawn, they were just drawing this. And it said, label the activation energy or something. And the student said, from here to here. Look at the difference in the graphs. This one's wrong. Why is it wrong? Okay. Yeah, so maybe going all the way down, maybe this one, here's what I'm looking at. Does anybody else have a suggestion before I say it?
Looks like it's on good.
Well, you're right, it's not labeled, but I don't think that was the issue. What's that? Yeah, so this is what it looks like. It looks like on this graph that the activation energy is from here to here. That's wrong, because that's not the activation energy. They're in the right part of the graph, but they're saying that the activation energy is here, and that's just not quite enough energy. So it's not quite getting there, the reaction never actually starts. And so the recommendation at this conference was have the students draw a dotted line. This is where the potential energy A is. This is where the activation energy is. So we've got these two well-defined lines, and then making sure that your arrow is touching both the lines or at least close enough where they can see this is what I need. Okay, so the potential energy of the activated complex. And the activated complex is talking about if I were using catalyst. So if I'm going to use a catalyst, how exactly does it affect this graph? Any guesses? What's that? It'll need less activation energy. So basically, if we add a catalyst, it's only going to require maybe this much activation energy. Activated complex. I know you're using one color. Sorry. And so the activation energy for this one, I won't clutter it up with more arrows, but it would only be from here to here. So from there to there, we've lowered the activation energy. It's going to require a lot less. I don't have any great examples of how you can use a catalyst in a campfire. The only thing I can think of, and this is not a good example really, is gasoline. Gasoline is used up in the reaction, whereas a catalyst is not. At the end of the reaction, the catalyst is still there. Let's say you're going to light your fire with matches, and you have one match, and you light it, and you better get it right the first time. Or, I know some people who will pour, I don't know, maybe 3 or 4 ounces of gasoline, not much. Do it at home. Not smart. Just pour it on top of whatever firewood you have there, and then they take 3 steps back, and they have the matchbox here, and they have the match in one hand, and they and throw it. And what would take, a match lighting for maybe 20 seconds until it burns your thumb, it's just as soon as it touches it, it's just big fire. Like I said, gasoline is not really a catalyst, but it lowered the activation energy a lot as far as our whole campfire ideas. Last up is the enthalpy of reaction. And I think this came up, I think we were already shut down, so you might not remember enthalpy of reaction very well. I'm going to do enthalpy of purple. Enthalpy of reaction is H, or maybe you saw it as delta H. This is basically did we release energy or did we absorb it? So we already said that we released energy, right? So we released energy. It was exothermic. So here's what it looks like. The energy went from this point to this point. From here to here is the enthalpy of reaction. Forget what you already knew about enthalpy of reaction. Looking at just the graph, would you say it's positive or negative? Negative, because it's starting here and it's going down. And so, yeah, exothermic, our delta H, or our here, negative. Yeah, the enthalpy of reaction is from potential energy to negative potential energy. We already did this. Use a dashed line to indicate what happens when a catalyst is added to the reaction mixture. There's the green one. The catalyst. From this graph, why does the addition of a catalyst speed up the reaction? It creates an alternate pathway with lower activation energy. Longer before it's been last. So this is what happens, creating an alternate pathway that just has a lower activation energy. From this graph, how does the increase in temperature speed up the reaction when temperature increases? So here's how I usually draw stuff like this. When temperature increases, more molecules collide. Remember, that was the first thing that we needed. With enough energy, that was the second thing we needed. To overcome the activation. All right, so I'm about to stop. I'm not going to go into the kinetic energy distribution graphs yet, but something I want you to think about for tomorrow. Seeing graphs like this, I show all of you this kind of graph in Chem 1. This graph drawn for you. So this is a normal distribution. I want you to think about this before class tomorrow. What happens if I were to stretch the graph out this way to the right? So let's say that this is 0 and I want to stretch my graph that way as much as possible. I want you to think about what's going to happen to the other points on this curve if I'm pulling and stretching everything